So in this session, we'll understand measurement of strain. So as so far the resistance strain gauge is concerned, we have seen the basic principle of operation of the resistance strain gauge. We have understood the different types of resistance strain gauge and the factors or the necessary characteristics of a bonded type strain gauge. Now, in today's session, we'll be understanding how the strain is measured using the strain gauge and the electrical circuitry that will be involved with this measurement of strain. We'll try to derive it and see how it operates. Uh, as far as the strain is concerned, strain gauge actually measures the average value of strain. So, using a strain gauge, we do not get the so we get actually the average value of strain spread over the complete area of the device on which actually the strain is being applied. And we do not get a strain on a particular point using the strain gauge point. So we'll get actually the average value of strain that will be spread over a complete area on which the strain is actually being exerted, but we'll not be getting the strain at a particular point. So if we are actually trying to measure the strain at a particular point, so using the strain gauge, that's not going to be actually using the resistance strain gauge. That's not going to be actually possible. It may be possible only if the case is that of a uniformly uh, exerted strain on a particular uh, spread of area. Fine. Say for example, we are taking a big sheet of metal, and at each and every point the same amount of strain is being exerted, so the average value of strain will be actually equal to the strain at a particular point. So the strain gradient in that case should be constant and strain should be uniaxial, but that may not be the case every time. So we have to adopt a model that actually takes both those factors into consideration. One, uh, the strain gradient has to be constant, and two, the strain is uniaxial. Fine. Uh, so in that case, what we do is that the strain gauge is actually fixed or aligned in the same axis as that of the axis of the strain itself. That actually makes sure that the uh, midpoint of the strain gauge actually coincides with the point of interest where we are actually trying to measure the value of strain. Now, in case this now, as I am saying that strain gradient may not be constant. So if the strain gradient is not constant over the area of the gauge, uh, and we do not actually know its form, how is it uniaxial or not, what the gauge will actually read will not be the actual measurement of strain at that very particular point. So what we can do is that in such cases, normally the smallest practical possible strain gauge that we can think about will be much more useful as compared to a strain gauge with having larger gauge, uh, larger uh, gauge. Fine. So there will be situations where the direction and the magnitude will both be unknown, and what we have to do is that in such cases the strain measurement uh, has to be uh, made sure that we, we have to make sure that the strain measurement in three different directions is made to determine the maximum strain and also to measure the direction of strain. Fine. Uh, so it's not going to. So what is the thing is that uh, the strain gradient will not be constant always. The strain may not be uniaxial. We may not know the magnitude and the direction of the strain. So in such cases, practically a low gauge smallest practical gauge can be used for measurement of strain. So that might be approximately giving us the true value of the strain at a particular point. But it's better to actually derive a model which actually makes sure that we'll be able to determine the maximum strain and the direction by using the three different direction measurement. So strain, uh, magnitude, and direction not possible to measure always accurately. Fine. So what we can do is that in such cases we'll take the measurement of strain in three different in such situations, in such cases strain measurement will be done in three different directions. So arbitrarily, we can take a 3D model wherein we can measure three measurement of strain can be done in three different directions. That may give us approximate value of strain. So the case here is that what we are actually trying to establish is that strain measurement at a particular point is not actually possible using a resistance strain gauge. Resistance strain gauge gives us the average value of strain spread over a complete area. So in order to actually find out the strain measurement at a particular point and find out its magnitude, find out its direction, we need to establish some uh, we need to establish some basic mechanic mathematics here for establishment of this very or calculation of this strain. So to measure now these three different strains in three different directions, what we can do is that we can take three strain gauges. Fine. So placement of three strain gauges for measurement of strain may not be possible uh, if we keep them uh, one over the other. Fine. If three different gauges are taken and the arrangement of these gauges is such that uh, they are one over the other, it is not going to be actually giving us uh, definitely in that case the gauge factor of these three strains, the dimensions of these three strains will be different. So it's not going to be satisfactory. It's not going to give a satisfactory performance, and measurement of strain is going to be difficult in such a case. So another way is to establish to arrange the strains side by side. Fine. Thus we can establish the strain gauge side by side so that portion of area can be covered. But with more portion of area being covered, we're actually again getting we're actually going to incorporate uncertainty again in the measurement because of the wider area being considered here. So to overcome both these cases, one wherein we are placing the strain gauge one over the other, and in another case where we are placing the strain gauge side by side, what we can do is we can actually make a what we actually do is that we make a strain gauge rosette. So what's a strain gauge? adopt a strain gauge uh, rosette. So what a strain gauge rosette is? So these rosettes basically involve a combination or an arrangement of wires, or we can say, or also foils in some cases. So an arrangement of wires and foils can be made in different ways uh, to form a grid-like pattern, so that measurement of strain can be covered at a particular point, even if it's spread over a larger uh, sectional area. We can measure strain at a particular point using this arrangement of wires and foils. So these arrangements can be done in different manners, and accordingly we have different types of strain gauge rosettes. So let me share the pics here. So these pics here, 7.16 shows a two-element strain gauge rosette. So it is a basic type of rosette. You can see a grid-like pattern formed by using a combination of two different wires. So that's why it's known as a two grid element. And the grid should be properly insulated with from each other. And then you can have a different combination like a delta rosette. You can have a rectangular rosette formed like these, a different set of coils. Uh, so using delta and rectangular rosette, what we can do is we can measure actually the measurement of strain is possible, even if the direction and magnitude are totally unknown to us. So by having this rosette, what we can do is that we can measure strain in any direction uh, with the temperature compensation also taken into account. Fine. Now, the grid actually at the strain axis will actually compensate for the resistance variation due to the temperature change, and uh, acco- and because of the strain, the resistance variation will actually be negligible in this case. Uh, so using this rosette, we have developed. What we can do is that we can measure strain gauge at a particular point. We can measure strain gauge. We are not actually measuring at a particular point. We are actually measuring strain gauge in different directions. We are measuring, as already said, we can measure strain in three different directions and accordingly derive the strain in a particular direction. Fine. So this is the basic practical strain gauge, that are actually how actually practically strain is measured using strain gauge. Now, what is the circuitry involved in this strain gauge? So we know now that what actually a strain gauge is. It's a transducer that actually will transduce the strain by known, that actually gives us a measurement of strain by known measurement values of resistance on application of strain. So uh, this resistance measurement needs to be checked, and how we can do that is by measuring the voltage change corresponding to this resistance change or the strain change. Fine. Um, so we can actually derive or use a potentiometer circuit or a bridge circuit. Uh, that will actually be a passive circuit, a passive type transducer. So an external excitation will be required. That will be actually giving us the actual value of voltage out. So what we can do is that we can uh, measure the value of voltage output corresponding to the change in strain, and accordingly derive the value of actual strain that needs to be calculated. So a ballast circuit is used in. for measurement of strain, for measurement of strain on application of resistance change. So ballast circuit looks something like this. So here Rg actually represents the strain gauge. R is an external resistance, or we can say the internal resistance of the external EMF source, and E naught is the output measured voltage. So as far as E naught, so as far this is actually a ballast circuit. So deriving the mathematical equation for this, as we derived in case of a potentiometer, E naught using a voltage divider law will simply be equal to Rg into EI divided by Rg plus R, or in other words, we can say A naught by E, let this be. So we have to differentiate uh, this equation, differentiate with respect to Rg. So d E naught divided by d Rg will be d by d Rg of Rg into EI divided by R plus Rg. That's nothing but d by drg of this is R plus Rg square, R plus Rg SA, d by d Rg of EI, uh, d by drg. EI is a constant term, so we can actually take it minus Rg EI d by drg of R plus Rg, d by d Rg of R will be 0, so it's actually dr g only again. So continuing, mm, which implies that d E naught divided by drg is equal to, while you make, this will be equal to EI R divided by R plus Rg whole square. Fine. EI RG DRG minus EI RG DRG, they will cancel out, and DRG, since we are differentiating with respect to DRG, so DRG term will be equal to 1 here. So in other words, DE naught is equal to EIR DRG divided by R plus RG square. DE naught is equal to EIR DRG, EIR divided by R plus RG whole square. Uh, we know that E naught is equal to EI into RG divided by R plus RG. That means, but E naught is equal to EI RG divided by R plus RG, or in other words, you can say EI is equal to E naught into R plus RG divided by RG. So substituting that here, we get dE naught is equal to E naught divided by RG into R plus RG into R drg divided by R plus RG square. Here the square and this term cancels out, so you have dE naught is equal to E naught R divided by R plus RG into drg divided by RG, where drg divided by RG will actually represent the gauge factor. So d naught is equal to E naught into R divided by R plus RG into gauge factor. Uh, so the value of R here related to RG will be large, so that it will act as a ballast resistance. In order to keep the current actually, uh, in order to keep the current high in the circuit constant. So irrespective of whatever the resistance of the strain gauge is changing because of the external circuitry, the current will remain constant. So the nominal value of R is actually 2 to 4 times the magnitude of Rg, approximately 2 to 4 times Rg. And why is that so? To keep current in the ballast circuit constant. So this is the ballast circuitry that can be used for measurement of resistance of a strain gauge. We can also measure resistance of the strain gauge using a Wheatstone bridge principle. So you already know in case of bridge circuit, uh, the equation is simple, and you can find out the opposite resistances balance out each other, and accordingly the device can be set for calibration. So without going into further, we'll actually wrap up the strain gauge, resistance strain gauge here. Uh, we'll do some numericals on the resistance strain gauge in the next session.